Hello everyone. My name is Michael Salin. I work for the French Network Information Security Agency, called ANSI. I'm going to talk about a project I started 2 years ago. So it's about hardening Linux, and this talk will be a bit focused on containers. So a typical attack scenario takes place, well, usually start by compromising a process or set of processes, and then gain more privileges, so elevate the attacker privileges to finally gain access to some sensitive data. So here we are going to try to harden user space to make the attacker work more difficult. So how to make something more harder? So of course you may want to use some good languages with some good security properties to avoid some common security issues. But you may use some legacy software or third-party software, so you may not be able to follow these good practices. However, you may want to follow the least privilege principles, which means to only give the rights to the set of processes which only needs these rights to the common, legitimate actions. And then you may use some compartmentalization techniques, like, for example, containers, or only using dedicated user for services. And here we're going to focus on containers. So for containers, there's some constraints and some pros and cons. What you want when you use a container is to have an abstraction from the host. So you may want to update your host in one time and update your container after that. So you don't want to sync and all these updates. So what's inside container image is maybe unique. So you need to have a security policy tied to this container, to the services running on it. And this security policy should be independent from the host, because the container is something standalone. Then, what we want for this is to be able to embed the security policy in the container image, to be, independent from the host. So, there's multiple ways to enforce security policy on Linux. Of course, there's the four major LSM, which are SLLinux, AppArmor, and Tomoyo, and Spark. All of them may be used to set some accesses on files or even network and processes, IPC. So they're designed to enforce access control in a fine-grained way. However, they're not designed to embed their own security policy in your container. So you have to configure the security policy for the whole host. Obviously, there's some works going on with namespacing LSM, but that's not here yet. And last but not least, you cannot enforce security policy if you're not running as root. So you need to be the system administrator to be able to enforce the security policy on your processes, even if it is an unprivileged container. So there's multiple other features available with Linux. A really interesting one is a seccomp, and especially seccomp BPF. So it is kind of a firewall to protect the kernel from user space. So as said in the documentation, it is not a sandboxing mechanism, but it helps reduce the attack surface from user space to the kernel. And obviously there is namespaces, which are the basis for containers. So this is not an access control system, but it may be used to only show some parts of the system resources, like only some file hierarchies or some subset of the network. But you cannot fully use all these features in an unprivileged way. Even if there's a user namespaces, it is not, you cannot use every namespaces features with it. And there may be some concern about some security issues. And another interesting point with seccomp is that you can embed your security policy, even if it's not a sandboxing mechanism, in your applications and in your container as well. So for example, there are some container managers which use seccomp BPF to harden their containers at runtime. So this is independent from the host. Obviously, the host needs to provide some features, but not the security policy. And then here comes Landlock. So Landlock is a Linux security module. So it is targeting fine-grained access control. So you should be able to enforce security policy on file paths and some more complex objects that you cannot do, for example, with seccomp. It is designed to be available for every user of your system, root user or even unprivileged users. And it is designed to be able to embed your security policy in your application, in your container, without being too tied to the host. So it is a way to create a programmatic access control. So now let's take a look at what Landlock may look like at first. So this diagram helps you give you an intuition of how it works. So in this example, the process sandbox itself. So it created a set of Landlock programs which are loaded in the kernel. And these programs are coded designed to filter some access to the system. In this case, these programs filter the open syscall. So every access to files with open or access or whatever. So this enforcement is only done for the process which enforces the security policy on itself, not other processes. So if this process is part of the container, this security policy only implies this process. So it is independent from the host. So there was some version of Landlock, and the last one will be the 8th version. So it is not ready yet, but it will be released in the following weeks. But I will give you an overview of what's inside this patch set. And anyway, I published an alpha release of this version, so you'll be able to check it and test it if you want. So this patch set for the Linux kernel is a minimum viable product, so it is only means to demonstrate that it may be useful for a lot of use cases, but without bringing too much code to limit the work of the kernel reviewers. And it is focused on file system access control, which is one of the most difficult kernel resources to enforce an access control on. And underneath, it is powered by eBPF. So what is eBPF? eBPF stands for Extended Berkeley Packet Filter. So it came from the classic BPF that you may know if you use TBDump or Wireshark to filter network packets. So eBPF is an in-kernel virtual machine which is designed to safely execute code in the kernel, and this code is loaded by user space and may be loaded by unprivileged processes as well. It is already widely used in the kernel. So for example, for the network filtering, seccomp BPF use it internally, and tracing, debugging, and a lot of other stuff. So there's two main important features provided by eBPF, which are really important and useful for Landlock. The first one is the ability to call arbitrary, well, not arbitrary, but dedicated functions, which are designed to be run from a specific type of BPF program. There's multiple types of BPF program, so there may be one for filtering networks, one for debugging, and so on. So there's also one for Landlock. And the other really important features is a new kind of IPC, which is called eBPF map. It is a way to store data, which may be available from user space and from an eBPF program. So this kind of a table, and there's a set of keys which are tied to a set of values. And of course, because this is, well, eBPF is meant to load code and run code at the kernel level. There is some security implication. So there's some security safety too. The main one is a static program verification at load time. So whenever user space load the program in the kernel checks a lot of things that the BPF program may do. Like, for example, accessing memory, and the kernel follow what the BPF program wants to do with this memory. So it taints the memory and do a lot of checks with that, which allow, for example, to restrict pointer leaks from the kernel. And obviously, there's an execution flow restrictions to only execute code from the BPF program and not jump in a number address in the kernel. So that's what is used in Landlock to express an access control rule. And what is used to enforce an access control rules is the LSM framework. LSM stands for Linux Security Models. So it is mainly an API to extend the kernel with code to enforce security policy on user space. There's a lot of policy decision and enforcement points which are scattered all over the kernel just before the code that may use some kernel objects. So for example, if you're trying to open a file, just before the open actions, there is a check to check if the current process is allowed to go through this path. And well, there's more than 200 hooks in the kernel, so it's quite complex. And all of them are quite specific to the kernel code, and they may evolve with the kernel code as well. So it's not a stable API, and it's done on purpose. With Landlock, the idea is try to bring some part of the LSM features to user space in a safe way and accessible to entrenched processes. So it's a bit different. For example, the idea of hook in Landlock is to define a set of actions on specific kernel objects. Like, for example, open a path, walk through a file path, or even open a network connection. So the programs are eBPF programs. Landlock programs are eBPF programs typed for Landlock. They are designed to check some access related to a specific Landlock hook. And triggers are means to restrict the way, to only run this program when they are designed to be run. For example, to only check read, write, or IUCDL actions, and so on. So now let's take a look at how we can write a Landlock rules. So a set of Landlock programs. So it's mainly eBPF. The easy way is to write the eBPF program in C. So actually it's not really in C, it's a subset of C, but it compiles with Clang, which is really useful. So you write your eBPF program in C, you then compile it, and you get an eBPF bytecode. Then you can embed this bytecode in your application, and when this application is run, is executed, the resulting process can then be able to load the eBPF program in the kernel. So let's take an example. So the example I will follow for the next slides is with two goals. So it is really a common use case to be able to access files in a read-only way or in a read and write way. But it's a bit more than only pass. It goes through file descriptors. So then we want this security policy to be enforced on a set of processes, and this security policy may be updated at runtime. So you can go check the code I just uploaded on this website, but I will explain right now some part of it. So to be able to enforce security policy on whitelist on of file hierarchies, you first need to create some whitelists. And actually, in the kernel, there's no way to express this for what is needed for Landlock. So the goal is to be able to list a set of files. But there's some challenges here. First, obviously, we want this to be efficient because there's a lot of access requests at the same time performed requested by a lot of processes. We want this whitelist to be updatable by user space at runtime to be able to add more files, more restrictions, or to remove them if you want to. And last but not least, we want this whitelist to be updatable and to be useful for unprivileged processes as well. So, for example, we cannot use extended attributes from a file system because extended attributes are dedicated to, well, can only be written by someone that is allowed to write on these files. So if you are in a read-only environment, you will not be able to write extended attributes. So that is a problem. And another constraint is that if you want to run multiple security policies in concurrencies, you want to compose them, so you need to be able to identify a file or file hierarchies for multiple security policies, which may not be run by the same user. So you need to be able to stack, well, to have multiple identifiers for the same files. So the idea is to create a new dedicated eBPF map. So there is already multiple eBPF map for multiple use cases. And this one take as a key an inode, which is not only the inode number, but the device as well. So it's struct inode from the kernel. So it is used by as a file descriptor. And the value is a 64-bit value, which may be used as a tag. So it is kind of independent extended attribute, independent from the file system. So with this kind of whitelist, we are able to identify a file, not a file hierarchies. But which is quite useful is to say, okay, this directory I want it to be available in a read-only way, but you don't want to list every file in it. So to express a file hierarchies, there is another feature from Landlock, another property. Landlock uses eBPF programs, but it can change them in a session. So there's multiple Landlock program type as well. The first one here is called FSWork. It is called for every work through a file path. So every directory you go through, this program will be executed on it. And in this example, I changed an FSPick program with the FSWork one. So the FSPick program is dedicated to evaluate, well, to allow the access or not to the leaf of a file path. So usually a file. And you can then add some triggers to only trigger this program for a subset of actions. In this example, open, changing directory, and getting attributes. So I created a subset of triggers which are related to read-only actions. And for write actions, I created another FSPick program, which is also triggered for when accessing a file, so the leaf of a file path. And this one will be triggered for write kind of operations, like creating a file, writing to it, or linking, unlinking, and so on. So how does this work? This set of programs are able to share a common value, which may be used to identify a state across execution of multiple programs. So let's see an example. In this example, so let's say we are in a container running as a web server, and the web server wants to access a file which is /public/web/index.html. So the first execution of the FS work program will be to allow or deny access to the first element of this path, which is the slash, the root of the file system. And at the bottom you can see the map which was previously loaded and set with 3 keys, /etc, /public, and /tmp. Each of these keys is tied to a unique value, which only makes sense for the program you only wrote. So in this case, I decide that the value 1 for read access and 2 for read and write access. So this FS work program, when executed, look for the inode, the file in this map. So there is no slash in it, so it just allows the path to go through, and then there's another one which is executed. So this FS work program is executed and can then look at which inode is requested. So the public inode is in the map, so the program knows that it is allowed to be used as a read-only for every read-only action. And then this program can then write in its context cookie that, okay, I saw a file which is allowed, a directory which is allowed. So for the next one, let's remember that we are in an identified file hierarchies. The next execution see the web directory. The web directory is not in the map, but that's a problem because we know that we are already in a file hierarchy, specific file hierarchy. And at the end, when we reach the leaf of the path, the index.html is not in the map. However, we still know that we are still in the file hierarchies, which is tied to the /public. And then the FSPIC program, which is tied to the open action, can allow this action to be performed. So let's take a look at how we can write this kind of BPF programs, Landlock programs. First, we need to define some metadata, some properties. So like I said, we need to tie a Landlock program to a Landlock hook. In this case, it is an FS hook. Then we need to chain it. In this case, it is the third FSPIC, the third program, which is the FSPIC, second FSPIC. And then it is tied to a previous one. From the user space point of view, you identify a Landlock program with a file descriptor. And then you can attach some triggers to this Landlock program. In this case, the append triggers, trace actions, and so on. So all of these are dedicated to write actions because I wanted to express this kind of actions. Then we need to write the actual BPF code. So it is here a subset, a snippet of the actual code. You can see it in the website, but it's interesting anyway. So the BPF program here is kind of a main function. And it takes as an argument a context. In this context, there is mainly 2 values. The first one is a cookie. So you can use this value to keep a state between different program execution. And the second one is the inode, which this inode you can then look if it is in a map or not. So here the first instruction is just to copy the cookie. The second one is to call a function. So this function basically look at the map, and if the inode, which is in its argument, is in the map, then it returns the tag, the value of the inode in the map. Otherwise, it just keeps the tag recorded by the cookie. And if the cookie contains a tag, well, which is allowed to write something, so it is here an arbitrary value, I think it's something like 2, then the program allows the action, otherwise the action is denied. So once you've written your Landlock program and the Landlock metadata, you need to load this in the kernel. For this, we use the BPF syscall with a prog load command and some attributes containing mainly the BPF bytecode, the BPF type, which is here Landlock hook, and then the metadata, which are tied specific to Landlock, as we saw just before. So the process called BPF program and load the program in the kernel. Then to apply this program to the current process, we use a second syscall. But we do not enforce second filter, we enforce a Landlock program. So here there is a new second syscall command, which is to prepare a Landlock program. And as arguments, we put the Landlock program. So it is a chain of programs. So we loaded the BPF program in the kernel, and then we can apply it to ourselves. So the process apply its own program to itself. So this process may be a container manager, for example, like the currency and so on. And then for every action that this process requests on the kernel, the workflow goes through the syscall entry point, then reach the LSM hook, which can then call the Landlock hooks, which are then tied to a set of Landlock programs, which are designed to be triggers for such an action. And then this program can allow or deny the requests and forward it to the dedicated code. So this enforcement is done for the current process, but not only this one. So let's see another example. Here we have a first process, P1, which is able to fork and create a new one, P2. But if this P1 process wants to enforce the security policy on itself, it can. And the new children from this process will then inherit this security policy as well. So it's exactly the same way as seccomp works with filters. And if the P3 process wants to enforce its own security policy on itself, it can too. So for example, if you're running a secure server in your container as P1 can enforce security policy for all the container, and the P3, so the web server, can also enforce its own security policy on itself. Or even if you want to run a container inside container, well, you could. You can enforce nested security policy. And obviously, the P4 process inherits from the P3 security policy and the P1 as well. Now, let's see a demo. So it's really a simple one. There's two kinds of whitelists which are configured by user space. The first one is a read-only set of file hierarchies which will be available in a read-only way. So for web servers, there's /public and /etc, /usa, and so on. And another whitelist, which is available, well, allowed to be written on. So the /tmp to be able to write some temporary files. But also for the example, I added the std.io, so std.out, which is identified with proc self fd1, so the first file descriptors. So let's see that. So let's say we are running as a web server user. So we are in the public directory. We can list the file there. So there is some junk here. That's not one. We can write some files. So here, for example, I write the file index.html. So that's common use case. So let's say it was the root user who configures the web server. And then we want to launch, let's say, a web server. In this case, it's a shell, but it's not different. So there's two variables. The first one is an environment variable to list the path which should be available in a read-only way. So you can see this /etc, other stuff, /usa and /public. And another variable is called llpath readwrite for read-write paths, which include the stdio, tmp, and so on. So this Landlock one program is a sample that you can find in the code. And so it is kind of a sandboxer or, well, a really light container manager. And so it will run the bin bash, the shell. So here we are in the new environment. So it is the same namespaces, but only with Landlock rules applied. So we are in the same directory. You can still list the files inside, but as you can see, there is some access which are denied. So you can see that the .. is denied. So .. point to the / directory, and indeed the / directory was not allowed to be accessed in a read-only or no write way. So we cannot get some info from this directory. However, we can get some info from the rest. And of course, if an attacker wants to write some files in the directory, it is not in a read-only way, so it is only accessible in a read-only way. And if we go in the TMP directory, we can list what's inside, and you can still create files, as says the security policy. And so as well, we can see the root, but if there is some private directory, we will not be able to see it as well. And so just to finish, as well, we cannot go to the root. So if we can enforce this on the root, obviously we can enforce this on arbitrary directories. So to wrap up, Landlock is dedicated to harden user space. So in a programmatic and embeddable way. So you can program your own access control rules as you wish and embed them in your applications for a set of processes, which is independent from the host. And one thing I didn't demo here is the ability to update the whitelist at runtime. So that's maybe really handy. And it is designed for internet use. So you may run it for any user. So currently, some patches, well, I made some little patches in the kernel to just prepare the landing of Landlock. So it's about 2,000 single line of code. Most of them are in the security Landlock directory, in the Linux source code. And well, you can follow the next, so the V8 patch series in the Linux kernel mail list or on Twitter. And I release the next one in the following weeks. So we can get some more information and we'll get some more in this website. Thank you.
Any questions?
So can this only be used to filter authorization to the file system, or can you also change the API call? What I have in mind is to be able, in a container, to have some user ID and to actually access the file system with another user ID, which means that you actually do some change to the API call, not just authorize.
Could you repeat this? Yeah.
Pas juste pour faire de l'automatisation, mais pour changer les user ID. De manière à avoir un user différent dans le contenu.
So, Landlock is dedicated to enforce security policy. So it is a new layer of security above the existing one. So if there is an SLinux security policy or even the DAC security policy, you cannot change it and you cannot map one UID to another. So for this, you may want to use user namespaces.
It's going to be a bit difficult trying to figure it out. Like, any other question? Like half the room is jumping already. So.
Yeah.
Looks like not. Well, thank you very much.